Hello, I am Jae-Young Park from Seoul National University, South Korea. It is a great honor for me to have this opportunity to give a keynote talk at ICRA 2020. It is very unfortunate that I cannot meet you in person. However, I hope that this online presentation can give you enough information and interaction. The motivation of our research is really about how to deal with uncertainties and disturbances when the robot is interacting with the real-world environment. So these videos were taken when we prepared for DARPA Robotics Challenge in 2015. So you can see the robot is driving a vehicle, drilling a hole in the wall, opening a door, and climbing upstairs. In all these applications, we may have some information about the environment, but not precise enough. So it is really important to deal with the uncertainties of the environment and disturbances from the interactions. There has been great progress in whole body control frameworks to deal with these problems. Compliant whole body control can vary depending on hardware and control approaches. For example, we may have a position control robot or torque control robot with or without joint torque sensors. And typically we do have force torque sensors at the limbs that are interacting with the environment. And we want to implement task priorities with many tasks. And these can be strictly a strict hierarchy or soft hierarchy, and many times inequality constraint has to be met. So there are many topics to be dealt with. In this very short talk today, I would like to focus on our experience using the hardware that we have in the lab currently. So luckily, we have two humanoid robots. One is a position control robot, and the other is torque control robot. These robots do not have joint torque sensors. However, we do have force torque sensors on the feet and on the wrist. However, we do not use them for control purposes yet. For control, we are using the operation space control framework, which is a strictly hierarchical control structure. So my research in this direction has started quite a long time ago. So on the left, you can see the manipulator is having two contacts on the end effector, and at the same time, the motion is controlled within the null space of the contact force space. And on the right, you can see that we have an additional contact on the third link of a robot. So at the time, the focus was more on the simultaneous and precise control of motion and force. And this control framework was extended to deal with floating-based robots. So very first equation is the equation of motion for in joint space, and that has a contact force because the typical floating-based robot has a contact force often with the feet to stand on. And from that, we can derive the equation of motion in joint space, in operation space, and operation space force can be computed using the dynamics. And we have to compute the actuated torque to be applied on actual actuators. So to do that, we are using selection matrix to account for unactuated floating base characteristics. And if there is a null space, then we can use the null space control to control the rest of the body other than the tasks. This was tested in a simulation at the time because we didn't have hardware to test it on. And you can see the ladder climbing, manipulation with walking was possible at the time that we can control the contact forces and motion at the same time on multiple contact points. Later, to deal with more tasks, we have developed hierarchical control task control structure with the sequence of null space projection matrices. Those are on the left. And when there is a contact redundancy, this is possible when we have multiple limbs are interacting with the environment. Then we can have a possibility that we can distribute contact forces without disturbing the motion of the robot. And balancing control is really, really critical, of course, for floating robot. So we really have to observe mid GMP condition and non-slipping conditions not to fall down. And this balancing control or this condition is met by sacrificing lower priority tasks in our control framework currently. So in the end, we can meet these inequality constraints while we can execute the higher priority tasks. So as a result, the result of this control approach is almost equivalent to the result from other control approaches, such as hierarchical quadratic programming approaches, because we are, in essence, meeting these equality constraints. And at the same time, we are controlling tasks with task priorities strictly. Hierarchical control. And this was tested on actual hardware. So on the left, you can see that we are controlling COM height as the highest priority task. And as a secondary task, we are controlling COM, horizontal motion, orientation, and swing foot. And when there's impact, CMP condition is violated, that swing foot is moving, not because of the impact force from the disturbance, but from the control force, because we are sacrificing the control of the swing foot to meet this GMP condition. On the right, you can see that the robot is stepping on unknown object, and it can compliantly step on this object and control the COM motion while balancing. So this shows quite well the main characteristics of using a torque control robot. In our case, we are using a current command instead of joint torque sensors feedback, because we do not have them. Very recently, we have developed a very reactive walking using these control strategies. So the main idea is that we are applying force on COM toward the swing foot. Swing foot is moving forward for walking. And we are monitoring the capture point of a robot. And when the capture point of a robot is on top of a swing foot, then we switch the swing foot to be a supporting foot and supporting foot to be a swing foot. And we are keep continuing this sequence to make it walk. And this creates quite reactive and compliant walking motion. So on the right, you can see that a person applies a force, and this force may be in equilibrium with the force on the COM, then the robot can stop in the middle of walking. So at this moment, the capture point is in between the 2 feet. That's why the robot stopped, and the robot can resume when the force is released. So this was very nice demonstration of compliant motion using a torque control robot. However, we may want to have accurate position tracking performance for some other tasks. So for example, we may want to accurately control position of feet or a COM. However, currently with our hardware and control framework, we cannot do it very well. So we are looking at this problem in various aspects: joint compliance, communication delay between main computer and motor drivers, state destination, modeling errors. Maybe all these factors are all linked together. So, however, we cannot attack all of them at once. So we are looking at joint compliance for now. And joint compliance is not a new problem in robotics. So there has been much research how to deal with joint compliance of manipulator in joint space control mostly. However, we think that humanoid has probably larger compliance on some joints, because the humanoid robot does not have large base, unlike typical manipulator. So this is because swing a leg sometimes has to be supporting leg, and supporting leg sometimes has to be a swing leg. And because of that, we have to design much lightly the legs, and the actuators are going to be smaller and have less stiff gears. And I think this is the main, we think that this is the main reason. And to deal with it, we are trying to use a simple approach first. So typically when we derive the rigid body dynamics of robot, we assume that the joint angle is the same as the motor angle, and then we derive this rigid body dynamics. However, when there's a compliance in between the motor and the link, these angles are different. So in our current approach, what we have done is that we use the link side dynamics as feed-forward control only, such as gravity compensation, and motor side dynamics is used for feedback control. So motor side information is used to derive the joint space dynamics, and from that, the operation space dynamics is derived to control the robot. And this was quite successful to increase the accuracy of position tracking performance. So you can see the difference between these two videos. And this was reported in last year at ICRA. We had another big problem with this robot. And the problem was that we didn't have the upper body. So whenever we call it a humanoid, people like comment that this is not a humanoid, right? What are you talking about? This is a two-leg robot. So we were not happy about these comments. So we finally designed and built upper body last year. And we have now new robot called 도깨비. And this robot is saying hello in Korean way. 안녕하세요. And we are very happy about this robot. And I really expect to have much nicer research result using this robot. Another interesting experience, research experience that I want to share today with you is using a position control robot. So when we participated in the RC DARPA Robotics finals in 2015, we didn't have a torque control robot. So we had to use a position control robot called Dormang from Robotic. For controlling this position control robot, there has been great research for position control robot, and typically using force torque sensors on the limbs, such as feet and the wrist. So we thought that we can just implement it, and then we can win the competition very easily. Not easily though. Anyway, and this was not possible for us because we had very, very unexpected problem. So robot had very large compliance on some of the joints, and those were hip and ankle. And the reason probably is the reason that I explained before, right? And because of that, we have deflection due to gravity, and this deflection creates a lot of problem for walking and other motions. So we had to take a look at what's going on with the actuator module, and we found that the gear has compliance, and luckily we found that this is quite linear, so that we can estimate this deflection from this linear model. So what we can do is we compute the gravity torque from the model of the robot. And then from the torque, we can use this linear characteristic to estimate how much deflection it is. And then we command additional command to the motors to compensate for it. And that was quite effective for slow walking. However, later when we deal with actual situation that the ground is not really flat, then it still has quite a vibration when we hit the ground and unexpected like object. So we had to finally install additional encoder at the joint to measure this vibration and use the ICRA control to suppress this vibration. And also we implemented disturbance observer, and very accidentally, what we have found was that we can use positive feedback of estimated disturbance. Then this was very, very nice for making robust walking. So the idea is that we estimate disturbance using a disturbance observer, and then we move the motor or command the motor in the same direction as the disturbance. Then it was very, very helpful for walking. So you can see on the left video that it steps on unknown objects, and then we estimate the disturbance, and we move the motor in the same direction as the estimated disturbance, and walking much compliantly. And in the second middle video and on the right, you can see that even having more like disturbances from the person or from unknown object, it can still deal with this to have robust walking. And this result was quite interesting because we are using a position control robot and even without force torque sensors. We are not actually against using force torque sensors. We are not ready yet. So this research using force torque sensors will be our future work. So I have shown today that our research on compliant robotic control approaches using these two robots, one torque control robot and the other position control robot. So before I finish, I would like to introduce other exciting research work in our lab. So we are working on many manipulation projects. So the Peginol task using two-arm, two-hand robot. So here we are using control based upon the operation space control framework. And we are trying to assemble an IKEA furniture using two Franca robots there. But I don't think this is enough. So we may have to use 3 or 4 Franca robots in the end. And we are also working on mobile manipulation control for many tasks and task transitions. Here we are developing based upon hierarchical quadratic programming approaches. And we are also working on telemanipulation using a humanoid robot. We participate on many interesting interdisciplinary research. So you can see that robot is acting as a red evil in art festival. We developed a rehabilitation robot for patients with lower back pain and drumming. And one of my really favorite projects was developing a CPR robot. During many experiments, we have revived many pigs. And I really hope that this is commercially really developed so that we can actually use it. So final project I want to introduce is our autonomous valet parking. So you can see that the car is entering a parking lot, and our autonomous car has a topological map of the parking lot and decide where to go. And when it is located a vacant parking space using vision, and it does motion planning, and using that information, it tracks the planned motion and park. And this was really recently demonstrated in our parking lot, and I'm really happy about this nice result. I would like to show our lab. So this is actually our lab with my students working very hard on our robot. And at the end of the day, they are hungry because they worked too much, and they're having ramen very, very deliciously. And this was on TV commercial 4 years ago in Korea. So finally, I really would like to thank all my lab members for their hard work. And also, I would like to thank you very much for listening to my talk today. Thank you.